Good morning, everyone, and thank you, Professor Nakamura, for the kind introduction, and thank you also to the organizers for inviting me to give this talk. It's a great honor. In this talk, I hope to describe some of our work on human motion measurement and analysis. And of course, this topic is of interest in many different fields, including biomechanics, neuroscience, and also application areas such as assistive devices and human-robot interaction. But today, I'm going to focus on rehabilitation. So why is there a need for human motion measurement analysis tools in rehabilitation? So current clinical practice in rehabilitation does not typically rely on any quantitative measurement tools. Typically, a therapist will assess the patient's current condition, recommend an exercise protocol, and then may personally and hands-on assist with treatment. And their assessment will be based primarily on visual observation and subjective feedback from the patient. This makes it very difficult to detect if the patient is doing the exercise correctly. It makes it difficult to assess the patient's progress, and it makes it difficult to assess the effectiveness of exercise protocols. So we would like to develop quantitative tools to help address these clinical needs. But there are a number of technical challenges to be addressed. The first one is motion variability. So of course we know that human motion is highly variable, but this is actually even more difficult in the rehabilitation setting, where we can expect not only variability between individuals, but also within the same individual over time, both due to short-term factors such as fatigue and also long-term factors such as disease progression or recovery due to treatment. We also have difficult measurement condition. So we may not be able to replicate our lab settings where we have perfect visibility of all the motion. In clinical settings and in home settings, the measurement conditions might be much more challenging due to issues such as occlusion and privacy. And finally, for many rehabilitation applications, it may not be clear what exactly we should be measuring, so what is relevant and important, and how we should provide that information to both the clinician and the patient. So in this talk, I want to talk about techniques that we've been developing looking at both lab and clinic environments and also home environments. So in the lab settings, of course, we've had motion measurement technology for a long time, but this technology has really focused on a kind of offline analysis. So first we collect the data, and typically the kind of data we collect is coming from motion capture. So we have the demonstrator is wearing a number of markers, which are observed by cameras that are placed around the demonstrator, and these cameras triangulate the positions of the markers to generate a very accurate measurement of the 3D positions on the markers. And then that data is typically post-processed, and then from there we generate the pose estimate or the joint angles. So I'll tell you a little bit about how to move from an offline treatment of this data into online treatment that can enable interactive applications. Once we move to the clinic setting, we may not be able to use motion capture because we may have issues kind of creating this large space. And then there are also issues with occlusion. So for example, if the therapist is helping hands-on, and also issues with privacy. So in the clinical settings, we've been exploring the use of wearable-based systems that we also use to generate a pose estimate for online pose estimation. And so I'll tell you a little bit about our experience developing these systems and also deploying them in the clinical setting. And finally, in home environments, we would like to have an even lighter weight sensor framework. So maybe we can leverage some of the existing technology with smartwatches and activity trackers, but we would like to move beyond simple activity tracking to generate more detailed measurements. But perhaps we can generate clinical metrics without pose estimation. And I'll highlight two projects that we've been working on in this area. One is looking at GAIT, and the other at symptom detection for Parkinson's disease. So let's start with lab and clinical settings. So in these settings, this is the system that we've been developing. So first we want to measure the movement, whether we're using markers or inertial measurement unit systems, so wearable sensors. From those measurements, we want to estimate the pose or the joint angles of the person at each time step. Once we have time series data of the joint angles, we want to extract the repetitions from that continuous data. So each time there's an exercise repetition, we want to extract when that repetition occurred. And then we want to use those repetitions to perform motion analysis. So to understand, did the patient perform the exercise correctly? Is their performance improving or degrading over time? And finally, we want to display and provide this information in a user interface, both to the patient and also to the clinician. So let me start with the first part of this system, and that is the motion measurement and joint angle estimation. So here we're particularly interested in online estimation. So we want to be estimating the pose as the measurement is taking place. And so we use a filtering framework. So our objective is to estimate the joint angles of a skeletal model. So we want to estimate the joint position, Q, the joint velocity, dQ, and the joint acceleration, ddq. And what we would, we integrate the skeletal model directly into our estimation framework. And so whether we're measuring markers in a lab setting or inertial measurement units in a clinical setting, we use those measurements and we incorporate them into the estimation by using the forward kinematics of the skeletal model. So we directly use our knowledge of the kinematics of the body in the estimation framework. We also use a prediction model. So in this case, what we started with is just constant acceleration. So obviously we know that human movement is not does not exhibit constant acceleration. So I'll come back to this point later. So we have a nonlinear measurement model, and therefore this is a nonlinear filtering framework. So we typically use something like an extended or an unscented Kalman filter. So in the lab setting, we typically use motion capture or marker data. So with marker data, we're measuring the markers at a very high frequency, and generally the position estimates of the markers are very accurate. However, there's still a number of problems. So one of the problems with marker data, especially when we're interested in online pose estimation, is that we can have missing markers that happen because of temporary occlusions. We can also have outlier markers, and markers can also be mislabeled from the motion capture system. So we can actually use our filter to help us address these issues. So every time we make a prediction about where the measurement will be, we have both a prediction of the measurement and also an uncertainty around that prediction. And we can use this uncertainty to reject outliers and also to perform automated measurement correspondence. So let me show you what that looks like. So here is an experiment of a highly dynamic motion. This is a person jumping. And in this first video, I will show you using kind of joint pose estimation without addressing these missing and occluded markers. You can see this generates a very unrealistic pelvis motion because during this motion, markers became occluded, and without addressing these issues, we get these significant errors in the estimate. So here is that same motion, but now using the probability of the filter to reject outliers and deal with marker mislabeling. So you can see in this case, we can generate a much smoother and more realistic looking motion, even though we have these occlusions. Let me show you now another motion where we have a very large number of markers on the body, and the person is moving in such a way to create significant self-occlusion. So you can see here that arms are being folded in front, and you can see how markers are just popping in and out as they become visible and invisible. And by using this automated marker reassignment, we can perform online pose estimation that gives us very nice and smooth-looking motion. Now let's move to the case when we're measuring with IMUs. So we can use the same general filtering framework, but now the measurement problems are a little bit different. So one of the issues with IMU measurements is that we're typically sampling at a much slower rate than would be the case with markers. And so here our constant acceleration model becomes an issue because it leads to a lag and incorrect joint angle estimates. So we would like to improve upon the constant acceleration assumption, but it's not clear how we could come up with a better generic model, because we know that there are significant differences between individuals, but also, particularly in the rehabilitation setting, there could be significant differences in the motion profile of a single individual over time. So what we propose to do is to actually learn the prediction model online during observation. And here we can leverage the fact that a lot of rehabilitation movements are periodic. So many exercises, and also particularly something like gait rehabilitation. So if we can make the assumption that our motion is periodic, we can formulate the structure of the model to be learned as a periodic model, so a sum of sinusoids. And now the learning task is to learn the parameters of that model, so that would be the frequency and the sinusoid coefficients. So since this is a very low-dimensional model space, we can learn this very quickly with just a few iterations. So let me show you an example of this system at work. So here what we're doing is we have a participant that is walking in place, and we're cueing their walking pace with a metronome. And every 15 to 20 steps, we change the frequency of the metronome. So that's what you see in the top graph. That each different color corresponds to a different frequency cue. And what you can see that the learned frequency and the learned phase very quickly adapt to keep track, to correctly model the change in the demonstrator's pace. On the bottom image, I'm showing the knee angle trajectories during this that were recovered with our pose estimation during this trial. So we can see here another advantage of using this periodic model. The model phase gives us a way to automatically segment the location of each stride in the trajectory, because each time we roll over to 2 pi phase, we know that this is the start of a new stride. And the phase variable, the continuous phase estimate, also gives us a way to temporally align the movements. So what we can see here is the knee joint angles that have been segmented and temporally aligned using the phase variable, which is plotted in the horizontal axis. And what we can observe during this trial is that this participant, in the first couple of steps, they are walking quite energetically. And so the knee angle amplitude is quite high. And then as the experiment goes on, they become tired and the knee amplitude decreases. So this example, of course, is this is some initial tests with a healthy participant, but we, of course, were interested to deploy this in clinical settings. So here I'm showing results of patient data, and this data was collected in collaboration with the Grand River Hospital Kitchener. And here what we did is we tracked stroke patients who were performing gait rehabilitation following their rehab. And we tracked them during the performance of 6-minute walk tests. So in 6-minute walk tests, the patient is asked to walk as far as they can for 6 minutes. So the measured data here, the orange, is the walking speed that's calculated from taking the total distance traveled and divided by the time of the test. The green results show the walking speed that's estimated from using our pose estimation results. So here what we do is we compute the joint angle, and then based on our kinematic model, we compute the stride, and then we sum up all the stride lengths over the entire 6 minutes, and divide that by the test length to get the speed. So this measure includes all of the sources of error in our system. So both the pose estimation error as well as the error in the kinematic modeling and the kinematic parameters. And we can see with the learned model, we can replicate the measured speed quite accurately, which seems very promising. Now, if we look at this data, it looks like this patient is improving over the course of the rehab because their gait speed is increasing. However, with our system, we can now look at the performance of this patient at the joint level. So if we look at the joint level recovery, what we see is that the patient is performing a compensatory strategy. So there is a significant asymmetry between their healthy side and the stroke-affected side. And what's happening here is that the patient is using a compensatory strategy. So they're using significant hip lateral rotation to avoid bending the knee. And unfortunately, what's happening with this patient is that they are not recovering a healthy symmetric gait, but rather over the course of treatment, they're getting better at using this compensatory strategy, which unfortunately is not the target of the rehabilitation. And this kind of analysis is not currently possible with current clinical setups, and this is something that we hope to enable. Now, this works very well when we have periodic movement. What happens if we don't have periodic movement? So if we have movement such as reaching that's typical during functional rehabilitation. So recently, we've been investigating the use of inverse optimal control to deal with this case. So inverse optimal control is a well-known method in both robotics and biomechanics. The idea is that we assume that the human motion is being generated in the central nervous system by an optimal controller. And our objective is to figure out what are the optimality criteria that are being used by the controller. So we hypothesize that the controller is a weighted sum of a set of features or basis functions, and then we try to recover the set of weights. And then in robotics applications, this is commonly used for to use that same controller for motion reproduction. However, the majority of the existing approaches assume that the entire motion has already been observed and pre-segmented, and then that complete motion is available during controller learning. But what we would like to do is we would like to recover the cost just from an initially observed part of the motion so that we can then use that model to predict what the rest of the motion will be and use this in our pose estimation. So in collaboration with Sandra Hirha's group at the Technical University of Munich, we've been developing a methodology to extract the model of the controller from incomplete trajectories. So what I'm showing here in this graph to the right is human movement data during a rehabilitation exercise, and showing the three joints. So this is a lower body exercise, the hip, the knee, and the ankle. The dashed lines are the actual measured motion data. The solid blue line is the part of the trajectory that we use for the inverse optimal control. And then the red solid line is the prediction based on the observations that we had from the first part of the trajectory. So in this method, we automatically figure out how much data we need for the accurate prediction, and then we use it for the prediction for the subsequent data. And I'm comparing here, the green line is by using standard optimal control methods, which obviously don't work as well because they're assuming that the complete trajectory has been observed. So once we have this kind of model, we can use it to improve pose estimation, even for tasks that are non-periodic. And of course, this is also could be quite useful for thinking about, so it gives us a short-term prediction of the motion that we can also use for other purposes, for example, anticipatory feedback, or thinking about things like assistive devices or exoskeletons. Now, I next want to talk quickly about the motion segmentation part. So I've already shown you how we can do simultaneous pose estimation and segmentation when we have periodic movements. But what can we do when the movement is aperiodic? So here we can also use this idea of inverse optimal control. So we know from the biomechanics and neuroscience literature that when a person is performing different tasks, the optimality criteria that are being used may change. And so we can use this insight to perform segmentation. So the idea is that we take a fixed sufficient size sliding window and we slide it over our observed trajectory, and in each window we estimate what the optimality criteria are being used. And whenever we observe that those criteria are changing, this is a candidate for a segment point. So let me show you some examples of doing this with human motion data. So here we have data from two participants that are performing a squatting movement. And in the top figures, you see the joint angles, and the square boxes indicate where exactly the movement is taking place. In the bottom images, you see the recovered cost weights. And what we very clearly see is that the cost function that is estimated during standing and the cost function that's estimated during the motion are very different. So this gives us quite a nice way to segment based simply on the changing of the cost functions. The other thing that's quite interesting here is that for these two different participants, it turns out that the strategy they employ seems to be quite similar. Now let's look at the final part of the system, and that is the user interface. So we wanted to see what kind of information would be important to provide to both clinicians and patients. So I'll focus here on the patient side. So we collaborated with Catherine Burns at the HCI lab at the University of Waterloo to develop this interface that we could deploy in clinical settings. So what you see here at the bottom inset is a video of one of my students who is simulating a patient, and this is testing with a very early prototype of the hardware. So as he's moving, we are using the sensors to perform online pose estimation, which you can see visualized as the blue leg in the image. And then we're also doing online segmentation, which you can see because we're using that to count the number of repetitions that the participant has performed. Now, we also show here a green leg, and the green leg is motion that was previously recorded, for example, by a therapist, and that is being used to provide guidance to the patient about what the motion is that they're supposed to be doing. And so the objective is for the patient to try to perform this exercise in such a way as to keep track as closely as possible to the green leg. So we initially tested this system with healthy participants, and what we find, as expected, is that the healthy participants, when they see this kind of visual feedback, they immediately synchronize their motion to the green leg. But we were interested to know what would happen if we tried this with patients. Because it could be that patients are very well aware of what kind of motion, what the motion is that they're supposed to be doing, but they may find it impossible to actually follow the guidelines because of pain or because of limitations in the range of motion. So we tested this system in collaboration with St. Joe's Health Center in Guelph, and we tested the system with 26 patients who performed their typical exercises following joint replacement surgery, either hip or knee. And they performed the exercises in the same session under two conditions. In the first condition, they performed their regular exercises while wearing the sensors without receiving any motion guidance, so not seeing the screen. And then in the second condition, they performed the same set of exercises, but now they were given this visual feedback. And we wanted to see kind of what would happen. So what you see here, when the patient is performing the exercises without motion guidance, you see this characteristic kind of they lift the leg fast and then they drop it down fast. So this is something that patients typically do to kind of make the exercise easier. So they jerk the leg up and then they use gravity to just let it drop down. And this is something that clinicians are trying to prevent, and they often give verbal feedback saying, you know, control your speed, control the motion, and so on. And we can see on the with motion guidance screen that the patient is able to use the visual feedback to perform the motion in a more controlled pace, and also we can see that they're able to increase their range of motion in the knee, which is one of the key objectives of this therapy. So this seems very promising because it seems that this kind of visual feedback can be very effective at getting patients to actually change their motion profiles. And this is with actual patients who are recovering from this surgery. Now, I want to talk about in the final part of this talk what we can do when we move from the clinic to the home. So in the clinical setting, it's reasonable to assume that we can place a sensor on each limb and then use the kind of system that I showed you earlier. But in the home, expecting the patient to wear a sensor on every limb, I think is unrealistic. Ideally, what we would like to do is to perform motion measurement analysis with a single sensor, hopefully leveraging some of the existing technology that is available in smartwatches and activity trackers. Of course, we would like to get more detailed information than the simple activity tracking. So if we could do this, of course, there's a number of advantages. We could do day-long collection, so we could find out what the patients are doing both during their rehabilitation activities, but also during their regular everyday activities, because those activities might be contributing or hindering recovery. We could collect data in much more natural settings, so in the home, outdoors, at a much greater convenience to the patient because they wouldn't necessarily have to come to the clinic. However, the disadvantages is that now we're relying on the patients to mount the sensors, so we can expect a lot more variability in terms of sensor placement. We also may have issues with lack of observability, so if we're only wearing the sensor on a single wrist and the patient, something interesting is happening in the other hand, we may not be able to observe it from the wrist of the other sensor. Of course, we can expect much poorer data quality than what we can get in the lab. And then we also may have difficulties labeling. So we may get a lot of data, but it may not be clear what the patient was doing during this time. So I want to highlight two projects that we've been working on to try to address some of these challenges. So the first one is looking at GAIT analysis. So with gait analysis, what we would like to do, gait information is quite useful for a number of clinical applications, including predicting fall risk and also tracking disease progression for a number of both motor and diseases such as stroke and diabetes. And there are a number of important clinical parameters that are already well known, so such as stride variability, stride symmetry, that does not require pose estimates. So in collaboration with Bill McIlroy's lab in kinesiology at the University of Waterloo, we have been investigating whether we can generate these gait parameters from the raw sensor data without requiring pose estimation. So here what we do is we use the same idea of these periodic models that we learn from data, but rather than learning over the joint angles, we learn directly over the measurement signal. And so you can see an example in this graph. So we have a patient who is wearing a single sensor at the ankle attached to their shoe. And first we have to detect when they're actually walking. Once we detect that they're walking, we then start learning the model of their gait. And you can see in this example is that the model is learned within approximately 7 steps. And then once the model is learned, we can start estimating these gait event parameters, gait events. So we collaborated with Professor McIlroy to collect data from patients who were using these sensors in their home. So they were walking down hallways in their own house, and we looked at a variety of residential settings, including independent living, assisted living, and also medical facilities. And so patients were walking in their own shoes, at their own pace, in their own home settings. And we applied this system with over 100 patient trials. We find that we can achieve average convergence within 4 cycles and generate 4% gait event localization error, which significantly outperforms the currently available methods. The final project I want to talk about is a recent collaboration between our lab and the Technical University of Munich and the Schön Clinic. And here we've been looking at using the single wrist-worn sensor for doing symptom estimation for Parkinson's disease. Parkinson's disease is a disease that's characterized, it affects the motor system, and it generates these characteristic symptoms that are known as bradykinesia. So we have stiff, restricted movement that may be accompanied by a tremor. And that's what you can see in this video. Now, these symptoms are treated with medication called levodopa. However, this medication needs to be very carefully dosed because if too much medication is given, patients suffer from this kind of over-medication symptom called dyskinesia. So these large amplitude uncontrolled movement. So what we would like to do is from a single sensor that's worn at the wrist, estimate what are the symptoms that the patient is feeling. But we want to do this in everyday living environments. So here I'm showing 2 patients that are seated, but during the course of the day, the patient might be walking, they might be preparing food, they might be eating, and so on. And so I want to just highlight 2 challenges with this type of data. The first one is when you the confound of daily activity. So we see this characteristic tremor, but we can imagine during the daily activity, the person might be whisking eggs, which could look very similar to the sensor as tremor. And on the other hand, we have this observability issue. So notice this during the dyskinesia symptom, when you look at the whole body, it's very clear that this is dyskinesia. But the patient is resisting this symptom, and they're pushing their hand, the one that's wearing the sensor, into the armrest. And so the actual motion that's observed at the arm that's wearing the sensor is much lower than the rest of the body, so it may be much more difficult to estimate this from the single sensor. So we collaborated with the Schön Clinic to collect a data set of 25 patients who wore this single band at the wrist in daily living conditions, and they were followed by a clinical expert who labeled their symptoms in every 1-minute interval. And our objective is to try to estimate the symptoms in these very short intervals. So this is we have a very high variability in terms of the activities of the patients, in terms of where they wore the sensors, and of the symptom severity of patients. So if we use this data, with classical methods, so something like support vector machines or convolutional neural networks, the classification accuracy that you achieve is still quite low, so 78%. So we've been thinking about how we can perform data augmentation that is robust to the symptom label. So one important insight is that the symptom label is invariant with respect to rotation. So where the sensor is located on the body does not impact the symptom label. So we can improve our classification performance and improve robustness against this placement variability by introducing augmentation with various random rotations. And also by modifying the temporal location of the symptoms, which is kind of which is generated by the labeler, we can further improve our accuracy and increase the data set size. So we can get up to 87% accuracy, and this is looking at leave one participant out, so on a new patient that has never been seen by the classifier. So this system seems quite promising if we can get this high accuracy of symptom detection for helping improve medication protocols for patients. So I want to end my talk by thinking about directions for future work. So I'm interested in thinking about how we can leverage both the learning and our knowledge of the skeletal kinematics to improve pose estimation, and particularly whether we could do it for more limited sensing. So even just having a single sensor or a couple of sensors at the end effectors. More fundamentally, I'm interested in what metrics are of importance. So do we need pose estimates, or there might be, for many rehabilitation and other applications, metrics that do not rely on the pose estimate. And finally, we saw from our initial clinical trials that visual feedback can be quite powerful at getting people to modify their movement. But there may be many different types of feedback, both post motion and also anticipatory, that could be used to further improve people's motor performance. So I want to end my talk by thanking all my collaborators, both clinical and academic, and particularly the staff and patients who contributed their time to all the studies that we performed in clinical settings. I want to thank all my students and postdocs, and finally our government and industry sponsors. And thank you for your attention. Yeah, so this is an excellent question, and one that we've been looking as well. I didn't speak about that work here, but you're absolutely right. The patient recovery is very individualized, and it's not monotonic. So even within a single patient, you may have setbacks, and then recovery, and so on. So one thing that we've been looking at is kind of generating metrics that give us the kind of patient current status with respect to some norm. And eventually we would like to move to a norm that's normalized to the patient age and conditions and so on. But in the initial work, we've just been using a healthy norm. And we can actually see, so one of the studies that we did is we looked at kind of using this kind of metric and then correlating it to kind of clinical variables. So an important clinical variable is the discharge. And what we find is that even with these very simple metrics, you can actually have once the patient's performance approaches that of a healthy norm, it's very strongly correlated with the discharge. So actually it seems like this is what clinicians are observing as well.
It depends on the initial state, as a patient might be just walking before the surgery or actually running. The goal won't be the same. So
yeah, so there's two different questions. The question is, is the patient recovered sufficiently to be able to walk unassisted? Exactly independently, versus is the patient recovered to their previous 10 years pre-surgery state. So I think those are two very different questions. I think to accurately answer that, ideally you would have data from the patient pre-injury, And hopefully, with, if we move towards systems where we're collecting data continuously, this is something that might become available in the future. But obviously, we don't have that currently.
Okay, and then I'll let the other person ask this question after. So here you talk about detecting tremors and trying to link it to the disease behind. But what about actually also measuring like wrong balance in the hips? Because, for example, some people actually don't balance properly their weight, and at some point it involves hip inflammation and other health issues. What about this? Do you envision these cases in your study at some point, or is this...
So do you mean in the context of Parkinson's disease or in the context of other
people, like more in general, like you go to the doctor and you say, okay, I have this inflammation and this. Is there would there be a study behind to say, okay, let's try to see first if actually you actually work well, or is there...
Yeah, so we've been looking at these kind of questions about gait analysis in the context of the elderly population, so not necessarily Parkinson's. And this is exactly one of the things that we're interested in, is to understand if we have this model of the gait, the measurement profile, and the gait events, can we use those to then correlate to disease progression or outcomes. And so this is actually something that's ongoing with this data collection in collaboration with Professor McIlroy. So we're collecting data from elderly residents of these multiple settings and collecting the data over time so that we can see whether, so the question is kind of what should we be measuring and what is predictive of these types of hip degeneration and so on. And I think this is something that is not yet answered. So this is something that, it's a very good question and something that we're also working towards. Thank you.
Go ahead. Just a question. By changing the degrees of freedom, for instance, in the knee and the hip, I assume that you might need to use that flexion. Do you find with changing the results, for instance, increase the knee degrees of freedom in your forward kinematic?
So let me just make sure I understood the question correctly. So you're asking is whether the choice of the kinematic model structure impacts the performance?
Yes, well, just the results. For instance, in your knee, I assume you're using mainly flexion, that you actually use, for instance, in rotation and other degrees of freedom as well.
Yeah, so we have definitely investigated various kinematic structures, and it depends on the task. So we also have a project that I didn't mention here, working with orthopedic surgeons who are looking at ACL. So with ACL, the knee abduction is very important, and so we can use the exact same framework that I described here, also to with any kind of kinematic model that we want to choose. And so for that different application, we've used a different kinematic model. Now, more fundamentally, the question is, what's the best model for each application? So currently, we're just doing that by a kind of a, we use our a priori knowledge that the clinicians provide of these degrees of freedom are important for this task. But there's a very interesting work from my colleague Zhenshan Venture looking at automated approaches for correctly selecting the kinematic and the dynamic model. So this is something that we're also very interested in. Thank you.
Okay, sorry, can I ask as well? So you were talking about the difference between motion capture and using inertial measurement units. So when you went to inertial measurement units, I saw there's a poster about choosing the location of where you place your inertial measurement unit to determine the pose of a robot pose. Have you found that impacts your measurements for measuring the human's pose of the leg as well? And where is the best position?
That's an excellent question. And in fact, knowing the pose of the sensor with respect to the skeleton, particularly the orientation of the IMU, is very important. So in all of the clinical studies that we do, so we've done quite a detailed sensitivity analysis to understand what are all the parameters of the skeletal model that impact the pose estimation accuracy. And especially for the kind of more slower movements that we see from patients, the orientation of the sensor with respect to the skeleton is the most critical. And so what we have developed also is calibration techniques that allow us to quickly identify these parameters during a clinical collection. And so this is definitely a part, so with all of these results, these important parameters are ones that we also estimate. And usually we do that in a so before the person starts moving, when they put the sensors on, we ask them to perform a couple of test calibration movements that we then use to recover these parameters.
Okay. All right. Thank you very much.
Thank you.